The following Tesla patent, and which is an original Tesla patent, falls under the very interesting category of high voltage engineering. It explains not just how to build a Tesla coil, but how to tune your Tesla coil with apparatuses which are regulating the totality of the circuit, in which you will have a Tesla coil which produces more electricity than there is put in. He writes, it concerns a method or improvements and methods of regulating apparatus for producing currents of high frequency, of which the following is a specification reference being had to the drawings accompanying and forming a part of the same. In previous patents and applications, I have shown and described a method of and apparatus for generating electric currents of high frequency, suitable for the production of various novel phenomena, such as elimination by means of vacuum tubes, the production of ozone, Röntgen shadows, and other purposes. The special apparatus of this character, which I have devised for use with circuits carrying current in the nature of those classed as direct, or such as are generally obtainable from the original circuits used in municipal systems, household systems that is, of incandescent lighting, is based upon the following principles. The energy of the direct current supply is periodically directed into and stored in a circuit of relatively high self-induction, and in such form is employed to charge a condenser or circuit of capacity, which in turn is caused to discharge through a circuit of low self-induction, containing means whereby the intermittent current of discharge is raised to the potential necessary for producing any desired effect. So here it means that the intermittent current of discharge, this means of the capacitor, when the capacitor discharges every time, it is said to be intermittent current of discharge. It is then raised to the potential necessary for producing any desired effect, and this means that you will then achieve more electricity because of this intermittent discharging of the condenser than you put in to the circuit. That is the case because of the inductive relations of the totality of the circuits, that is, the working circuit and the charging circuit and the discharging that is the charging circuit and the working circuit. So, considering the conditions necessary for the attainment of these results, there will be found as the essential elements of the system the supply circuit, from which the periodic impulses are obtained, and what may be regarded as the local circuits, comprising the circuit of high self-induction for charging the condenser, and the circuit of low self-induction into which the condenser discharges, and which itself may constitute the working circuit, or that containing the devices for utilizing the current, or may be inductively related to a secondary circuit which constitutes the working circuit proper. So here it basically says that there are three parts. There is the first part, which will develop the high voltage. Then there's the second part, which is the supply circuit. The supply circuit for the working circuit, which is part 3. These several circuits, it will be understood, may be more or less interconnected, but for the purpose of illustration they may be regarded as practically distinct, with a circuit controller for alternately connecting the condenser with the circuit by which it is charged, and with that into which it discharges. Okay? And with a primary of a transformer, that's your Tesla coil there, and the latter circuit having its secondary in that which contains the devices operating by the current. To this system or combination, the invention subject of my present application pertains and has for its object to provide a proper and economical means of regulating. Therefore, it will be known that every electric circuit, provided its ohmic resistance does not exceed certain definite limits, has a period of vibration of its own, analogous to the period of vibration of a weighted spring. In order to alternately charge a given circuit of this character by periodic impulses impressed upon it, and to discharge it most effectively, the frequency of the impressed impulses should bear a definite relation to the frequency of vibration possessed in the circuit itself. Moreover, for like reasons, the period or vibration of the discharge circuit should bear a similar relation to the impressed impulses or the period of the charging circuit. When the conditions are such that the general law of harmonic vibrations is followed, the circuits are said to be in resonance or in electromagnetic synchronism. And this condition I have found in my system to be highly advantageous. Hence, in practice, I adjust the electrical constants of the circuits so that in normal operation this condition of resonance is approximately attained. To accomplish this, the number of impulses of current directed into the charging circuit per unit of time is made equal to the period of the charging circuit itself, or generally to a harmonic thereof, and the same relations are maintained between the charging and discharging circuit. any departure from this condition will result in a decreased output, and this fact I take advantage of in regulating such output by varying the frequencies of the impulses or vibrations in the several circuits. Inasmuch as the period of any given circuit depends upon the relation of its resistance, self-induction, and capacity, a variation of any one or more of these may result in a variation in its period. There are therefore various ways in which the frequencies of vibration of the several circuits in the system referred to may be varied, but the most practical and efficient ways of accomplishing the desired result are the following. A. Varying the rate of the impressed impulses of current or those which are directed from the source of supply into the charging circuit, as by varying the speed of the commutator or other circuit controller. B. Varying the self-induction of the charging circuit. So you will see that in the drawings, that is there the charging circuit is of high self-induction, and this can be varied. Varying the self-induction or capacity of the discharged circuit. To regulate the output of a single circuit which has no vibration of its own by merely varying its period would evidently require for any extended range of regulation a very wide range of variation of period. But in the system described, a very wide range of regulation of the output may be obtained by a very slight change of the frequency of one of the circuits when the above mentioned rules are observed. In illustrating an illustration of my invention, I have shown by diagrams in the accompanying drawings some of the more practical means for carrying out the same. The figures, as stated, are diagrammatic illustrations of the system in its typical form, provided with regulating devices. Of different specific character. These diagrams will be described in detail in their order. Okay, I will try to show you the invention now. Here it is. But I would like to say something. Here you see the generator, which is a motor in this case. And this motor may be of high voltage DC or AC, and this you can accomplish by yourself at home, because many people don't have a motor, and I don't have one myself as well. This can be put away and used you can use a flyback transformer from your television. And your flyback transformer will output DC, high voltage DC, direct current, which you need. But you can also use AC with a high voltage flyback transformer. If you do something with this direct current, you can easily make it alternating. But anyways, it will anyways be alternating, I think, because we will put a circuit controller. This what you see here is not only a source of direct current or alternating current of high voltage, but you have in the same moment also a circuit controller. Okay, this circuit controller will be to alternately open and close the circuit. Okay. So you can have your circuit controller built on a small motor with little pieces of copper, this and that, and let it turn around and make it alternately open and close your circuit. Of course, to come back to your flyback transformer will have to be driven by a driving circuit, okay, flyback driver. You can find flyback drivers on the internet. They are also called ZVS drivers, especially for flybacks. And these have the advantage that you can then run your system, your driver, on 9 to 12 volts batteries. Okay, so you don't need any wall sockets, 110 or 120 volts, 220 volts. You don't need this, you don't want that, you want to start off the grid. You have your battery, you have your driver, and you have your flyback. Alright, your flyback will usually output DC current, high voltage DC current, which you will interrupt with your circuit controller. That will be a motor with a circle on it, a disc, and this disc will be divided in segments of usually copper, but that is not the point here. You will have a good conducting material on the segments. The disc will rotate and interrupt the circuit. And of course you can very easily build something like a pulse width or a motor speed controller, which you then will regulate the speed of your circuit controller. Okay, so here you have your high induction coil, your high induction circuit. And now we go back to the patent. So you're off the grid, you are having your high voltage, okay, for basically nothing, 9 to 12 volts, and you're on your way, okay. So and each of the figures A and B, and I will have to put that aside a little bit. Okay. A and B is your line circuit here. Okay. Designates the conductors of the supply circuit of continuous current. A motor connected therewith in any of the usual ways and driving a current controller D. So your line circuit DC, driving the motor, it's a DC motor with a disc on it, which is your circuit controller once again, and also circuit controller D, which serves to alternately close the supply circuit through the motor or through a self-induction coil E. And to connect such motor circuit with a condenser F. So at the same time you will alternately open and close your induction high induction coil in the same frequency, in the same interval as your capacitor, because you will have, when the circuit is open here, you will be on the segment, and then the disc will rotate, and then at the same, well, just a moment after that, it will be the capacitor which is closed, okay, and that will be on and off. So this will be on, and this will be off, and this will be on, and this will be off. So we choose to alternatively close the supply circuit through the motor or through a self-induction coil E, and to connect such motor circuit with a condenser F. The circuit of which contains a primary coil G. Okay, come out of the capacitor, go into the primary coil of the Tesla coil, which will generate more electricity than we put in. In proximity to which is a secondary coil H, serving as the source of supply to the working circuit, or that in which are connected up the devices KK for utilizing the current. The circuit controller, it may be stated, is any device which will permit of a periodic charging of the condenser F by the energy of the supply circuit and its discharging into a circuit of low self-induction. So here you have the low self-induction, here you have many turns, high self-induction. But nevertheless there will be a relation between these two coils, and in reality I think this will be the length of the coil will be in a certain division or multiplication. In this device, in this case it will be a division of the length of the wire in this coil. In order to secure the greatest efficiency, so let me repeat that here, to store up, I therefore employ a motor of high self-induction, or in place of, or in addition to such motor, a choking coil or self-induction coil E, to store up the energy of the supply circuit directed into it, and to deliver it in the form of a high potential discharge when its circuit is interrupted and connected to the terminals of the condenser. So when the circuit controller will do that, this making this connection there, making with the condenser. In order to secure the greatest efficiency and a system of this kind, it is essential, as I have before stated, that the circuit, which mainly, as a matter of convenience, I have designated as the charging and the discharge circuit, should be approximately in resonance or electromagnetic synchronism. Okay, and this indeed happens through the length of the wire, which should be a certain division of each other. Moreover, in order to obtain the greatest output from a given apparatus of this kind, it is desirable to maintain as high frequency as possible. Okay, this can mean two things in my opinion. That is, you try to have a source with as high frequency as possible, which can be a flyback from an old TV, which produces several thousands volts. Or it can be the frequency of the discharge of the condenser. Any case, as high as possible, the electric connections, which are now well understood, have been adjusted to secure, as far as practical considerations will permit, these results. I effect the regulation of the system by adjusting its elements so as to depart in a greater or less degree from the above conditions with a corresponding variation of output. For example, as in figure 1, I may vary the speed of the motor and consequently of the controller in any suitable manner, as by means of a rheostat L. Now I think that is this one here. Okay, so if we translate that to the flyback, we use the flyback as the source of high voltage direct current. Okay, then you can basically before the flyback you have your driver or your ZVS, and the ZVS or driver you can easily make with a frequency regulator on it, a simple pot, that is simply a regulator and regulatable resistor. So you adjust the frequency here, right, and we have a separate circuit controller, has nothing to do with our flyback. We can regulate that because on this controller you can control the speed of the circuit controller, and we have two controllers there. So, for example, in figure 1 I may vary the speed of the motor and consequently of the controller. So here it's the same thing, but in any suitable manner, as by means of a rheostat L and a shunt to the motor or to such motor, or by shifting the position of the brushes on the main commutator. And a commutator is basically you have the shaft of a motor, and on the shaft you have a disc, and this disc has segments, and this disc can be used to run the motor itself, or it can be used to be a circuit controller. So if you thus vary the speed of your motor, you vary the frequency of your on and off circuits, and thus the timing of your discharging of your capacitor.